All right, so the homework tonight is the 3s and the 4s, which there's 2 of each. And today we're going to continue on by talking about different laws, and on Monday we'll talk about a principle. Now, the things that we're talking about today and Monday deal with volume. It's some type of relationship with volume. So the first one is Charles' Law, and this is a temperature-volume relationship. And let me go to the little graphic there. So looking at the two graphics here, as the temperature increases, what happens to the motion of the gases? They increase. They get faster. They actually expand. They get farther away from each other. As the temperature gets lower, they get slower. They don't move around as much, so the volume decreases. So as the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. And this is a before and after scenario. So we look at what the volume was initially, and then what the volume was at the end, or vice versa with temperature. And here's a nice little graphic. Did you guys get all the blanks up there? Okay. Here's a interesting thing. This is a tanker car for a train. I don't know where this picture was taken, but I do know the story behind it. This tanker car actually carries some type of liquid, and it has to be periodically cleaned out. Obviously, it's during the wintertime, even though we don't see any snow on the ground, but the temperatures are cold outside, or the absence of heat is lacking in this scenario. And what happened was the cleaners went in, the people went in, steam cleaned the inside of it, and as they were cleaning it, they somehow, some way closed the pressure valves to not allow for the air to go in and out, or the change of pressure. So when they finished up steam cleaning the inside of it, obviously it was pretty warm on the inside. They closed up the hatch, sealed everything up, went home for the night, came back, and this is what they saw. Okay. Now, here's what happened. Inside the tanker car, it was obviously much, much warmer with the water vapor that was present. And so as the gas inside cooled down, what happened to the volume? It got smaller. And as you decrease the volume, we'll talk about this later on, as the volume decreases, the pressure inside gets lower, but the outside pressure doesn't change. So as the pressure inside the tanker car got lower, the atmospheric pressure just said, okay, wham, just crushed it. Once the gases got small enough and the pressure said, okay, we're going to do this, then it collapsed on itself. Yeah, and I would guess it's at least a half-inch thick. Probably more, but no less than a half-inch thick. On a tanker car? I'm sure there is one. So here is the a tanker, and it doesn't take long once the pressure inside goes. Ooh, nice music too.
Wow.
Oh, it looks like an experiment.
That's the exact same one.
Nah, it didn't have Eva on there. Practice problem. For 2. All right, so here are the calculations that we're going to be working with. We'll have a volume, initial volume over initial temperature relationship, and then we'll have a final volume over a final temperature relationship. Or we'll have the temperature over the volume relationship. Okay. Now, depending on what you're looking for, whether we're looking for a final volume or a final temperature, depends on which of these two equations we're going to be using. And these two do represent for Charles' Law. And when you're working these out, my suggestion is, let me scoot this up a little bit. When you're working this out, as you're working this out, write down the variables as you're reading the question. So, for example, let's use the blue here. So a sample gas occupies a volume, there's V1, of 100 centimeters cubed at a temperature, T1, of 200 Kelvin. What volume, question mark V2, would this gas occupy at a temperature, T2, of 150 kilopascals? And then at the end it says the pressure and the amount of gas do not change. That'll mean something later on, but it doesn't really mean anything now. So since we're looking for V2, should we use the equation here on the left or this guy? The one on the left. So let's move this one out of the way for just a moment. Okay. So, and we always have to do this. We don't ever want to cross multiply, so we want to manipulate the expression before we do anything. So since we're looking for V2, I want to get all the known variables to one side of the equal sign. So I know V1, I know T1, I know T2. So I want to multiply T2 on both sides. So again, as I talked about earlier in the year, if I have a variable that's on the other side of the denominator and on the other side of the equal sign, just put it on the top. Okay. So in this case, my equation now looks like V2 is equal to V1 times T2 divided by T1. Once you have that, lug and chug. That's the difficulty of this. The hardest part is determining, okay, do I use this equation or the other equation? Which variable am I looking for? And then go ahead and just tell yourself what the variables are. And then from here, we have 100 centimeters cubed, T2. And this is one reason why I like writing T1 and T2 so I don't accidentally write the T1 in the wrong spot. Okay. So if you don't do that, that's your gamble. And then divided by 200. And then you should get a value of around 75. All right, what I have in the box is the minimum I need to see to get full credit. Okay. In other words, show me the variable we're looking for, the unknown, show the variables rearranged, the knowns, and then showing the work within. Is this difficult? I don't know. Pretty bad. Let's move you over just for a second. Questions on that? You got that, Celeste?
Yeah, I actually do this now.
Isn't that awesome? All right. So let's look at the next problem. Okay. So the next practice problem says, okay, you all right? Okay. The next practice problem says if a sample of gas occupies a volume, so there's V1, 0.325 liters at a temperature, there's T1, 30 degrees Celsius, 30 degrees Celsius. What temperature, question mark, T2, will the gas be if the volume changed to 200 milliliters? Now, first of all, which equation should we use? The one on the left or the one on the right? We're looking for T2, right? So we want to make sure we use the equation that has T2 on top. So always make sure that the variable you're looking for is in the numerator or on top.
It doesn't matter which side.
No, it doesn't matter which side. But make sure that, you mean side left, right? Yeah, it doesn't matter there. But just make sure numerator, denominator. So we want to use the equation that we have here. And so let's manipulate. Okay. So let's rearrange. So we're going to multiply and get all the known variables to one side. So now my equation looks like this. T2 is equal to T1 times V2 divided by V1. Now, as a heads up, make sure that if you're looking for like a temperature, that you actually have a temperature in the numerator so that the unit itself is actually on top, not an inverse value. Okay. Put you over there. And then looking at the numbers, to be able to cancel out units, they have to be the same unit. So here, my volumes, I have liters and milliliters. Doesn't matter, yeah, so you choose. It's up to you. If you want to go change the liters and the milliliters, that's cool. If you want to change the milliliters and the liters, that's cool. Okay. I like liters, so I'm going to leave this alone. So my V1 down here on the bottom is 0.325 liters. But how many liters do I have in 200 milliliters? 0.2, very good. So you have, and again, some of you, we're still having some issues with this. There's 1,000 milliliters in a liter. Okay, so don't forget that. So that's a 0.2 liter scenario. All right, the temperature is in degrees Celsius. That's bad. So in that case, we're going to go 30 plus 273, because again, we have to get it to the Kelvin scale, because if we have a negative degree Celsius and you don't change it, you're going to have a negative volume. And that critter just does not exist. Okay. So 30 plus 273 is equal to 303. What is it?
Wait, we're just getting back. Where do 303 come from?
Right here.
Because you can't do this with the Celsius, you need it in Kelvin.
Right. So since we're in degrees Celsius, you must convert it to, what is it? 1/8, yes. And colors. So again, what is in the box is the minimum. Okay, for full credit.
So Kelvin is just 273.
Correct. And we did that in the ones, I believe. So if you need to go back and look at that, you may. All right. So the threes are part of your homework. All right. Good old Boyle. Ooh. This is where it starts to hit the fan. No, it'll never hit the fan today. All right, Boyle's Law. Boyle's Law is a pressure-volume relationship, and I like using this analogy. Right now in this room, we're going to pretend you are a gas particle. Okay, so you're pretty relaxed. You've got your own space in this classroom. You're doing pretty well. All right, now what I need you to do is to, all of you, get in that cabinet. Okay? Every one of you, get in there. Okay. Now, here's the thing. The reason that seems like, oh, man, that doesn't seem like a good time, is because we're actually compressing. So as you compress all these gas particles together that are nice and relaxed here, and we compress them together, I'm going to have to exert a great amount of pressure to get you all in there and keep you in there. And then you might feel that pressure as a result. It'll be a bonding session. How's that? You like that? So, when we talk about Boyle's Law, as the volume goes up, the pressure goes down. Very good. Okay? And then vice versa, if, what did I say, pressure first? Okay, so as the pressure goes down, then the volume is going to go up. So it's inversely related. So if it's inversely related, we get a really nice equation. It looks like this. P1V1 is equal to P2V2. Okay? So when you have direct relationship, we divide. When it's inversely related, we multiply. Okay, cool? And again, the pressure, the P, the V is the volume. Were there blanks on this one? Good, I like that. All right. And let's go to the practice problem. And there's a lovely graphic there from the 1930s. That one's not mercury. Those are gas particles. Quit talking about them. All right, so let's go through this first sample question. Says a sample gas has a volume, V1, when the pressure, P1. What is the volume, question mark, V2, of the gas when the pressure, P2, and the temperature and amount of gas remain constant? Okay. So which variable are we looking for here? So we're looking for V2. So that means that I'm going to divide by P2 on both sides. So my equation looks like this. V2 is equal to P1 V1 divided by P2. And all the units are the same. How convenient.
I have a feeling that's never going to be like that.
Sadly, they will be. There's not much I can do to manipulate Charles and Boyle's equation. I can change the pressures up a little bit.
Charles and Boyle?
I may do that on the homework.
Wait, this homework that we're about to do?
No.
I'm not taking this class in 5 years.
You're not taking the test in what?
I said I'm not taking these classes in 5 years.
Oh, well, you never know.
You're going to be a sophomore in college.
I don't want to take it, no matter what.
Questions about that?
Ooh, 70
Look at me using same numbers, different units. All right, try number 9 on your own, and don't peek up here. Don't peek. And here I did change some things, so you have to have a like values to cancel them out. So don't leave milliliters as milliliters and liters as liters. Convert one to the other. So I'll work it out up here. Don't peek. All right. So don't look. Don't peek. This one's brutal. I know. Are you guys done?
I knew you wouldn't put milliliters.
Yeah. Shh, you should be working right now. Thank you, Celeste. Are you done, Celeste? Oh. No. Am I doing it? I don't know. Are you doing milliliters? I'm going to do milliliters. All right. I'm going to do milliliters. There's a what? That I like. That one I like.
Hey,
Multiply 5.5 by 1,000.
you didn't see that. How many atmospheres are in 1 milliliter?
I don't know. That's really small. What did you say, Celeste? I don't know. You were the one doing it. What'd you get?
Craig, I'm not done.
4, 5, 6. Yeah, I got 45.6.
45.6?
I'm not done yet. Please stop.
And that is millimeters of mercury.
Not correct.
Mr. Craig, I don't think that's right.
You don't?
200 answers to the example. That's not what you have.
What do I have?
0.06. I got 45.6.
Yeah, we all got that. Just a minute.
Yes.
Whoa, is that even the same problem? 1 atmosphere.
Oh.
That's not even the same problem.
Yeah, it is. It says find final pressure and atmospheric pressure.
He's already looking at that point.
Oh, it does say an
Check
atmosphere.
that in their answer, boy, because I just
What is a fine? Oh, very good, Celeste. Nice. So we got to convert that to atmospheres. Yeah. Celeste, way to read that question.
Even Dr. Craig.
No, I didn't read the whole question. Dad nabbit.
Nice.
Sorry, I used those words in front of you.
200 times.
That makes me angry that I use those words in front of you. I feel terrible. Oh, I know. It'd be my last day. All right, now we got an answer. Let's try this. Because, again, it says in atmospheres. Duh. Did you get a number? What about 3 sig figs? Yeah, you're just looking at...
3 sig figs?
Yeah, 3 sig figs.
Oh, hold on, I'll type it in. I got 0.059969. No, it is 0.06. It's just 0.06. There's no other sig figs in it. 0.06. 0.06, yeah. 0.06.
Where are you getting at?
Am I calculating?
All right, I'll go with that. I like Luke's answer, but I'll go with that. All right, so the homework, the 3s and the 4s, might take you about 10 minutes, but don't wait until Monday to start it.